Hello, in this tutorial we're going to be looking at application of integral calculus in kinematics. In kinematics, there are two main quantity that we're going to be looking at, so which are the velocity and also secondly the acceleration. From elementary physics, we define velocity as a time rate of change in distance. So we have the formula for velocity v to be equal to change in displacement over change in time. So from this expression, we can see that velocity is a function of time. So it changes as the time changes. It's also shown in the definition that velocity is the time rate of change in distance. So if we define velocity as a function of time, you can have that f of t equal to ds over dt. So if you have this, which is function of t, f of t equal to ds over dt, you can cross multiply it to have ds equal to f of t dt. So, and we define our s as the displacement, while t is the time. So knowing that s is the displacement and t is the time, so to find the displacement here, we can take the integral of both sides. If you are not familiar with it, we only look at this while looking at integral calculus. So if you take the integral of both sides, integral of the left hand side and also the integral of the right hand side, we're going to have s, which is the displacement, to be equal to integral of f of t dt. And if you find the integral of f of t dt, we're going to have s, which is our displacement, to be equal to, using capital letter now, t plus c, where c is the constant of integration. So here, from our velocity relationship, which is velocity is equal to ds over dt, we're able to get a formula for displacement using integral calculus, and can get the value for c using the initial conditions. So we are going to see how we can go about this in an example. So that's how we can go from velocity to displacement. So the same thing applicable to acceleration. We define acceleration from basic physics, that acceleration a equal to change in velocity over change in time. So acceleration is simply defined as the time rate of change in velocity. So you have this to be dv over dt. So you can also see clearly from here that acceleration is a function of time. So if you make acceleration a function of time, we represent this as g of t. So acceleration is represented as g of t. So this is change in v over change in t. So again, if you cross multiply, we are going to have dv to be equal to g of t dt. So again, taking the integral of both sides, we're going to have our velocity phi to be equal to the integral of g of t dt. And from our basic integration, we know that here we have v to be equal to, using the capital letter notation now, g of t plus c, which is the constant of integration. So again, we are able to get a formula to represent velocity using integral calculus. Again, we are going to have our c from initial conditions. So these are the things we have to take note in applying integral calculus in the field of kinematics. So we started working with velocity and acceleration, and from velocity we are able to get our displacement, and from acceleration we are able to get the velocity. So let's look at an example on how we can manipulate this to produce a solution of kinematics. Here we have an example to better illustrate the concept of application of integral calculus in kinematics. The question says that a particle is projected in a straight line from a point O with a speed of 6 meters per second. At time t seconds later, its acceleration is 1 plus 2t meter per second square. Find the velocity and its distance from O when t equal to 4. So in this particular example, we're looking for two things, which is the velocity and also the displacement, which are what we look at in the illustration of application of integral calculus in kinematics. So for the first part, we are looking for the velocity. We are looking for the velocity when t equal to 4 seconds. If I go back to the question, we have that a particle is projected in a straight line from a point O with a speed of 6 meters per second. So I have my initial speed. So when t equal to 0 seconds, that's the initial speed, I have my velocity to be equal to 6 meters per second. So you take note of some of all these facts in the question, and at time t seconds later, its acceleration is 1 plus 2 t meter per second. So when t equal to t seconds, we have the acceleration to be equal to 1 plus 2t meter per second. So now I'm to find the value for the velocity when t equal to 4 seconds. So from the illustration, we define that acceleration equal to change in v over change in t, which is change in velocity over change in time, and then we are going to have the v over the t equal to the acceleration according to this question is 1 plus 2t. So if I have our acceleration to be equal to 1 plus 2t, here we can have that the v is change in velocity equal to 1 plus 2t dt. And by integrating both sides, using the concept of integral calculus, we are going to have v, which is our velocity, to be equal to the integral of 1 plus 2t dt. So what we need to do here is to find an expression for the velocity so that we can also work on the initial velocity. So how do we calculate the velocity here? We are going to have the velocity, I've just used v, equal to integrating this, we are going to have this to be t plus 2t squared over 2 plus the constant of integration, and this also equal to t plus t squared plus c. So we now have our velocity v to be equal to t plus t squared plus c. So this is an expression for velocity. Whereas we are looking for v when t equal to 4 seconds. But before that, we have to use our initial condition, as I mentioned in the example, to get our c. So we're going to get the c using initial conditions. And what is the initial condition here? If you go back to the first thing we wrote here, so we have that at t equal to 0, v equal to 6 meters per second. So we are going to be using this as our initial condition. So these are initial conditions. So we can now come back to our expression and said v is 6, which is 6 equal to t, which is 0 plus 0 square plus c. And then we're going to have our c to be equal to 6. So we now have c to be equal to 6, and we can rewrite our expression for velocity to be equal to v equal to t squared plus t plus 6. And here we have the expression for velocity. So from where we can now find the velocity when t equal to any number. So what we are looking for here is to find v when t equal to 4 seconds according to the question. So we can substitute t to be equal to 4 in this expression. So we have our velocity to be equal to 4 square plus 4 plus 6, and this is equal to 26 meters per second. So we have our velocity when t equal to 4 seconds to be equal to 26 meters per second. So if you are familiar with our last tutorials on integral of calculus, so we look at definite integral where we have to consider the lower limit and the upper limit. But in this case, we are not considering the issue of lower limit or upper limit, because we have to find definitely the velocity when t equal to 4 seconds. And we already have our initial condition t to be equal to 6 meters per second when t equal to 0, so which is v equal to 6 meters per second. So now let's look at the second question, which is to find the displacement. If we go back to the question, we have the distance from O when t equal to 4 seconds. So from this question, we are looking for the distance from point O to point when t equal to 4 seconds. So therefore, we are considering the lower limit of 0 and the upper limit of 4. So from the last solution, we had that v equal to t square plus t plus 6. So this is the expression that defines the value for v when t equal to t seconds. So and from the illustration, we have the velocity to be equal to change in displacement over change in time, which is change in distance over change in time. And then we can have our ds to equal to v dt. Integrating both sides again, we are going to have s is equal to t, the integral of v dt. In the case of our example, we are going to have s is equal to the integral of our velocity at time t equal to t seconds equal to t squared plus t plus 6 dt. So since we are integrating from point O to point when t equal to 4 seconds, so we have our lower limit is 0 at t equal to 0. So let me define this. T equal to 0, and we are calculating all to when t equal to 6 equal to 4. So the upper limit equal to t equal to 4 seconds, 0 seconds. So you can find our displacement s from 0 to 4 seconds, t squared plus t plus 6 dt. So integrating this, we are going to have t cube divided by 3 plus t squared over 2 plus 6t over 1. So integrating from 0 to 4. So substituting the upper limit, we're going to have this to be equal to 4 to the power of 3 over 3 plus 4 to the power of 2 over 2 plus 6 to the power 6 to the 4 minus, and then we substitute 0 here. If you put 0 here, 0 here, we're going to have everything by right hand side to be equal to 0. So this now leaves us with 64 over 3 plus 16 over 2 plus 24. And then we are going to have this to be equal to 63, 64 over 3 plus 22. If you have 64 over 3 plus 22, we are going to have 2 here 1 and 2 here 8. So adding 8 with 24, we are going to have this. This to be 32, yes. So adding 8 to 24, we are going to have 32. And adding this together, we are going to have this to be equal to 160 over 3 meter. So we have our displacement after t equal to 4 seconds to be equal to 160 over 3 meter. So and this is how we can apply kinematics and also integral calculus. So this is the application of integral calculus in kinematics. So thank you very much for joining me in this tutorial, and I'll see you in the next tutorial.